Can you see? Hello?
Yes,
Hello?
sir.
Yes,
Is
sir.
it changing? Is it changing or is it showing first page only?
Changing, sir.
Okay, fine. So today we'll start the Huffman coding problem. So see the object. This is really nice problem solved by the Huffmans. So according to his name, it is known as the Huffman coding problem. So what is the problem? The problem is that you are the sender. Okay, you are the sender, and you you will send a message. Okay, and there will be a receiver. So to transmit the message, so there is a cost. So there is a
Sir, you're not
cost.
audible. Sir.
I'm not audible. Hello,
Yes, sir.
am I audible?
Yes, sir, you're audible.
So there is a cost. What is the cost? Cost is the transmission cost. Okay, the transmission cost. So transmission cost means the cost incurred to transmit the message. So if you means you see how you will represent the characters. Suppose you are representing A by say 110 like this. Say B is 010 like this. So you see if a message contains uh, A B, then for these 3 bits and say it is like this 4 bits, so 3 plus 3 plus 4, this is the these many bits. So actually the cost of transmissions depends on the number of bits that you are transmitting, because each message consists of some letters. So you are representing each letter by some bits so therefore the cost of transmission is in terms of bits. So how many bits you are sending. So how can you do something so that the transmission cost is reduced? So that you see you want to store a given 10,000 character data file, and data file contains only 6 characters. So I am saying that you are sending a file which consists of 10,000 sorry 1 lakh characters, and the file contains or consists of only 6 characters A B C D E F, right? And frequency in thousands means this occurs 45,000, this 13,000 like this. Okay, so if it is so, then the binary code encodes each character as a binary string or code word over some alphabet, means A B C D E F. So code is a set of code words such as these 000 or 001. What is this? That you are representing these by A, you are defining, that depends on you. And this is suppose G like this, or A, whatever it may be, means each for each character you represent this. And these are the, or you can represent like these also, means single bit represents this represents say B, this represents a C, like that. So if you represents the bits, then and scan the message and replace the character by the code words, what will happen? You see, if the code is like this, A B C this, C1 A is this, B is this, C is this, then the word bad will be encoded as B means 01, A means 00, and D means 11. Clear? Now if the code is like this is one example. Here you see all the code, means these and these, they consist of two bits, means this is, you can say that fixed length encoding. Here you see, in this case, please mute, who has, please mute your button. So this is a C2. Another, means if you represent like this, here you check A consists of 1, B consists of 3 bits, C 2 bits, this. So this is the variable length encoding scheme. So in this case, you see, bad will be encoded as, you check, BAD. Now, when you will transmit the message, the receiver will get this message and he will decode what is this. 110 means, you check, it will say, okay, it is B. Then it is 0, 0 means A. And if it is 111, it is G. So it will do like this. Now, here you see, in there are two methods. One is the fixed length encoding and another is the variable length encoding. So fixed length encoding forward means has the same length. Variable, I have said, the different length. So you see, in fixed length you can represent it like this: fixed length code and the variable length code. Now when the receiver will get a message, means a set of strings, and if it is a fixed length, means 3 bits, 3 bits, 3 bits, so it is very easy to interpret by the receiver to meaning of the message. Means he know that first 3 characters, the next 3 characters stands for another, next 3 bits for another character, next 3 bits for another character, next 3 bits for another character. But in variable length code, you see, if you get a string of bits, then how can you know that, means here you see, if it is 1, you check, one states starts, means one, if it is 1 first, you are reading 1, so the rest of the characters may be like this, say 101. So you see 10, so it may be 10, maybe B, 10 maybe C, or a part of B. Yeah. So in this way, so there should be some property so that the receiver can decode the message if the variable length coding is used. Now here you see, if each bit consists, if each character consists of 3 bits, then fixed length coding will take these many bits, because 1 lakh characters are there and each character needs 3 bits. So 3 lakhs bits are used to store the file in case of fixed length coding. And if variable length coding is used, so you see, it occurs 45 times, A occurs 40, not 5, 45,000 times. These occurs 13,000 times, like this. So how many bits will be required? For A, you see, number of bits is 1. So 45 into 1. For B, 3 bits. So 13,000, actually 1000 is common, is taken as a common. So in this way, you compute the number of bits required to transmit the message. So it needs, you see, all 224,000 bits. And here it needs more bits. So in this case, space is saved. So now how to represent this, means how to create a variable length code. So a message is to be uniquely decodable, that I was saying. When you are sending a message, the receiver should decode the message uniquely. See, in this case, there are 3 variable length coding schemes. Check it. Example. So it is, sorry, it is fixed length 00011011. But these 2 schemes are of variable length. Now for C1, you see, for if the this is the string, so I know in case of C1 means fixed length, C1 is the fixed length. So what will be the how it will decode? So you see, you take scan first 2 bits, then next 2 bits, then next 2 bits, because it's fixed length. C1 is fixed length. So 01 means B, 00 means A, 11 means D. So it will be BAD, bad. Fine. Now If you use this C2, then here you check 1 1. In this case, you see 1. Does there exist any character which has 1, only single 1 here? No. Okay. You see 1 1. Destiny 1 1. Does it occur? Only two ones? No. 1 1 0. 1 1 0. Yes. So it is B. Fine. Then 0 single 0. Yes. A. So it is A. Fine. Then 1. No single 1. No double 1. Triple 1. Yes. It exists. So it will be D. So it is uniquely decodable. Means this is also uniquely decodable. Now if you use C3, means this scheme, then you check it is single 1. Then see single 1. If it is single 1, then it can be A also. Check it. So that's why it can be A. Fine. And then it can be, you see, 1 0. Next 1 0 stands for C, so it can be C. Then 1 1, so a single 1, just take single 1, so it is A. And the last 3 ones are D. So it can be ACAD. Or if anybody reads like that, first 3 characters, means first 3 bits, 1 1 0, that will stands for B. Okay. Then next one single 1 A. Then triple 1 D. So D. So that means receiver will be confused whether it is bad or ACAD. So that means whenever you should use a encoding scheme, the encoding scheme should be in such a way that the receiver will be uniquely receiver will be able to uniquely decipher the meaning of the message. So that means this here you see C1, forget about C1 because that is the fixed length encoding. This is the costly. We know already. Now this, among these there should be some difference so that we can use C2. There should be some difference, means you see C3 it doesn't give unique. It doesn't give unique. No, it is not giving unique message. So it is giving unique message. So what is the property? Here you check one thing that is called prefix property. Here A occurs, here a single bit 1 is there. Fine. And here also the first bit is not first bit, but here actually just a minute. Here its prefix is saying that no bit should be the prefix of the another character. You see here a code is called a prefix if no code word is prefix of another one. That means you see this example here is not a prefix but it is a prefix code. Why? In this case you see a code is called prefix code if no code word is a prefix of another one. See 0 is not the prefix of any of this. You check this 0 does not occur at the first 110. You check it 110, does it occur as the prefix of this? Does it occur? That is the prefix of this. For example, see I am writing here, say there are two symbols. X is say 10 and Y is 101. Now here you see this 10 occurs here also at the first of this symbol Y. So this is the prefix.
Excuse me, sir. What you are writing is not visible, sir.
Can you see
Yes,
my
sir.
pen?
No, sir, we can't.
No,
Sir,
sir,
we can
your
only
pen
see
is
your
not.
cursor, sir. Only see your
Can you see
cursor,
this
sir.
all these cursors? Okay, you
Yes, sir.
see here in this case. um, okay, if I change the color, just a minute. Can you see now? Yes or no?
Sir, only the cursor, sir. Nothing else.
Only the cursor. Okay, so there is some problems. I know. I do not know. So you please see the example then. I am just mentioning in the cursor here. You see, uh, in this case, in the first example, you see that A is 0 and C is 0 1. So what is the first symbol? First bit of C? 0. So 0, you check, is 0 a code word for another character in this example? Yes, for A is 0 and for
Yes,
C
sir.
is 0 1. So therefore, in the means A is the prefix of C. Check it. A is the prefix of C. So means it is a subset and that is occurring at the first. So therefore, this is not the prefix code. A code is called a prefix code if no code word is a prefix of another one. In next example, you see none of the code
Sir, we can't
occur.
see the second example, sir. You have to scroll down a bit, sir, actually. The last example is not visible, sir.
This is not visible.
No, sir, no, sir. The bottom is not visible, sir. It's like A equal to 0, B equal to 110 is visible, but beneath
Then
that it's not visible, sir.
C is 1 0
No, sir, it's not visible, sir. C
in the
zero
same
1 is
line.
visible. Sir, we can see A equal to 0, B equal to 110, C equal to 0 1, D equal to 111, but not the one where I'm guessing C is equal to 10. I'm guessing C is equal to 10, sir, but we can't see that, sir.
Just a minute. Just a
Sir, I
minute.
think your aspect ratio is a bit off, sir. Could you, if you like made the window
Okay,
smaller,
I okay.
a
Just a minute.
little.
Just a minute. I am.
Yes, sir. Now it's visible, sir. Now it's visible, sir.
Okay, here you see what I'm saying, that these A, see here I'm just giving an example. X is suppose 1 1 and Y is 1 1 0 1. Now in this case you see this 1 1 is occurring here, means Y is basically what? Some X then some bit. Say here this is 0 1. Is it not so? If it is so, you see, then it is called the prefix. X is the prefix of Y. Okay, so if it is present in the scheme, that is not the prefix code. In this example, check it. That 0 is occurring here at the first of C. If it is so, it is not the prefix code for the scheme. And in that case, the receiver will be confused when he is getting some 0 first, whether it will be A. Means if it is like this, suppose you are getting a message like this, whatever it may. So you will be confused to check whether it means whenever you are reading 0, getting 0, then you will be confused whether it is A or C is starting. Clear? So that means this is not the prefix code. But if there are no such character whose code word is a prefix of another one, that we will call the prefix code. In this case scheme, you check it. Means if it is 0, for example, if you are using this system, whenever you are reading it is 0, immediately you will say, okay, it is A. I don't need to check what is the next character, because 0 does not occur as the prefix of any other characters. If you are reading, say, suppose 1 1 0 1 1 1 like this. So when you are reading 1, does there exist any 1 in this case? First single one, no. Then 1 2 ones are there, no. 1 1 0, does it occur? Immediately I am saying yes, 1 1 0 occurs, and I am sure that this is not the prefix of another character, so automatically I am sure that these three must represent B. No other way. In case of prefix code, if it is prefix code, then immediately receiver will decode this message as the B and then something else, for example B and D. Clear? There will be no ambiguity. So how you will do that so that there will be no ambiguity and the cost is minimized?
Sir, one question, sir.
Yes.
Sir, you in the beginning of the slide, sir, it's written that fixed length codes are always uniquely decipherable, sir. What is
Fixed,
the reason?
it is not fixed length is always you know that I have to give a marker just after every 3 bit.
Okay. We have to give a marker. That's why we can decipher. Okay, sir. Okay, sir. Yes, sir.
Marker means suppose I am
Yes, sir. You
saying
can.
you
You
that
know the length. You know the length, so you
length.
can divide
I
it.
know. I know that is the scheme uses 3 bit length, or I say 4 bit length, or say 5 bit length. Now, what is the problem in that case? Suppose I am saying that I am Sanjeev Sadhu. I do these. So you see, letter is used so many times. Its frequency is so many times. Clear?
Yes, sir.
And there are some letter, for example, Z. Z is used less frequently. Now, if you use the fixed length coding for each character same, then what will happen? Then that means that its cost is say Z. But if you use variable length coding, then the character which occurs so frequently, you generally use minimum number of bits for that, so that the cost will be reduced. Are you getting? The suppose if I represent the letter I by a single bit and I use so many times, then the length of the bits, total bits, will be reduced, and the Z which I am using less frequently, its length should be larger because I am using that very small amount of time. But in case of fixed length coding, what happens? All the characters are given same importance with respect to the number of bits. So no code word is the prefix of any other, so we can always find the first code word in the message. So here you see, if it is the so, then a first 0 means A, then 1 1 0 matches, then 0 1, like this. So therefore we should be interested in finding the good prefix free codes. Now given an alphabet A1 A2 A3 AN with frequency distribution, means this is the strings, and the frequency is this for each character AI. Then you are finding out a binary prefix code C for A that minimizes the number of bits. So what will be the number of bits? This A of AI into the length of this. This is the length of CI. Okay. Prefix code C and this I equal to 1 to n. You see where CI is the code word for encoding AI and the length of code word CI. Suppose we want to store the message made up of 4 characters A, B, C, D with frequency. It has been given. Percent means you see 60 plus 30 plus 5 is 100. So A occurs 60 times, B occurs 5 times, C occurs 30 times, D occurs 5 times in a 100 character message. Okay. So fixed length, you know that if there are 4 different characters, then I need 2 bits to represent each one uniquely in case of fixed length encoding. And the prefix code, I am representing A, B, C, D by variable length encoding. You see, one is in this case 0, in this case a single bit, 3 bit, 2 bits, 3 bits. to store these 100 characters. So fixed length code requires how many bits total? 100 into 2, 100 characters, and each character needs 2 bits, 200 bits. And the prefix code uses how many times? 60 into 1. You see, 60 into 1, 5 into 3, 30 into 2, 5 into 3, 150 bits. So 25% savings. Now the question is, how can I create the prefix code? So there will be see, I have drawn a tree, and just like A means 0 0 0 1. Left child, you see, left child is 0, right child is 1. Left child is 0, right child is 0 0 1 0 1. So if I reach here, then I am traversing 0 0. If I reach here, then I am traversing first 0, then 1. So this is 0 1 1 0 1 1. And in case of variable length, you see A was 0, like this. A is 0, B is 1 0, C is this, like this. So the binary string from path to the path from the root to a leaf is code word associated with the character at the leaf. So di
So
is
how are
the
we generating the binary tree, sir?
I will say that is the Huffman coding. That is the Huffman coding. We will generate. Say how. Di is the depth of the leaf AI. This is the notation. Depth of leaf, and this is equal to LCI, length, the depth of code word associated with that leaf. BT is weighted external path length of tree T, and that is same as B of C, the number of bits needed to encode the message with corresponding code C. If I, you see the frequency into depth for each character. Given weights F1A, this find a tree T with n leaves labeled A1, A2 dot dot up to AN. Just a minute. Given weights frequency with the frequency this, find a tree with n leaves labeled A1, A2 dot dot that has minimum weighted external path length. We have to find out this, and this is actually minimum weighted external path length means that you have computed already. That example, 100-bit character like this. So this is equivalent to Huffman encoding scheme. So Huffman, what is that algorithm that you are asking? Suppose S is the original set of message characters. Okay. So what we will do? We will first pick up the two smallest frequency. That means the letter which are used less frequently. Okay, from the S, and create a subtree that has two characters as the leaves, and label the root of this subtree as Z, and we will set the frequency F Z equal to Fx plus Fy. So that means what? Actually, you see there are so many characters. If I write like this, say this is A, B, C, D in this course, and it occurs say 25 times, it occurs 5 times, it occurs 3 times, it occurs 20 times, like this. Now these are the frequency. You choose the two nodes whose frequency is the least, smallest frequency. And what we will do, suppose B and C. So say this is C and this is B, and you will add them. So this is 5, this is 3, 5 and 3, 5 plus 3 is 8. Clear? And then you delete them, delete B and C. So remove X and Y. B and C means X and Y in this case. from S and add Z to S. What is the Z? Z is this. Actually, this is X, this is Y in the algorithm. So S will be S union Z minus XY. So that means S has just decreased by 1. You see, initially this was the set S. So repeat this procedure called merge with the new alphabet S until S has only one character left in it. Now whatever you will get, that will be called Huffman coding tree. So it encodes the optimal prefix forward for the given fixed distribution. See here, example. This is the S. A occurs 20 times, B occurs 15 times, C occurs 5 times, D occurs 15 times, E occurs 45 times. Okay, in the original character. And these are the frequency distribution. So you see which two are of minimum? C and D. Check it. C occurs 5 times minimum. D occurs 15 times. This is minimum among all this. You can choose C and B also, no problem. Okay, because both are 15. C and D are B and D are 15. So either B or D will be chosen at the first step along with C. So you see, and in you add this, I will get 20. Fine. Now you initially there were 5 nodes. 1, 2, 3, 4, 5. I have merged 2 into a single one. Now its weight is 20. So you remove these two. Now which twos are minimum? Here you check, this is 15 and this is 20, this is 20, 40. So 15, then you take either A or N1. N1 and say B. In this way you add.
Sir, could you go to the previous slide once, sir? Just once. Sir, the previous slide, sir.
This is the previous slide, first one, or just previous is previous. This one, algorithm. Is it okay? Hello? Hello? Hello?
Sir, one sir, sir, sorry, sir, my net had gone, sir. Sir, my net had, I'd lost my net, sir. So could you go to the next slide, sir, once? Just put the next slide, sir. Actually.
Yes, yes. Here you check it.
Yes, sir. Yes, sir, this one, sir. Okay, so next step after that.
A and B is merged.
Okay, sir. Recursively it happens. Okay, sir.
Yes. Until and finally you will get the single root. Means like this.
Yes, sir. Yes, sir.
And
Got
the
it.
final. Now what you will do? You assign 0 to the left child and 1 to the right child for each internal nodes. Okay. And now you see what is the code of this? A 0 0 0.
Zero.
A is 0 0 0. And B will be this one 0 0 1. 0 0 1. C will be 0 1 0. D will be 0 1 1. And E will be 1. Now here you see one thing. See, the frequency of the original characters were like this. A had 20, B had 15, C had this, D had this, E had this. Clear? So you see, E had maximum 45 frequency. Check it.
Yes, sir.
So that means E occurs so many times. So that so many times means if a character occurs so many times, and if you represent that by smallest number of bits, then you will be able to save the message, means save the cost. That's why you see E has only single character, a single bit. Check it. So that means the uh, letter which are used less frequently occur at the leaf nodes. Sorry, all occurs at the leaf nodes, means at the farthest from the root nodes. Its depth will
Yes, sir.
be larger. Okay, and this is actually used for compressing a message. Okay, that means this is the basics for that WinZip. You are zipping. WinZip, na, that compression. There are some modification anyway, but this is the basic. So, given the character with frequency distribution FA, the binary Huffman tree is constructed using priority queue, capital Q, with frequency as the key. And this will be the algorithm. N is S, Q is the for I equal to 0 to n minus 1, because at each level I am decreasing the number of characters by 1. I am merging. Na? Z is the new node. Extract minimum from the Q. Q is the priority queue. Okay. And extract minimum from another. So left, right, merge them. Frequency of left Z, frequency of right Z will be equal to this. And insert Q in the Q Z. So total running time will be n log n. You check it, because that means priority queue is heap is there. You know heap. You have to create that. And I think so. Time is not there, but I'm just telling using this lemma, you need to prove that it is gives optimal. Okay, every internal has exactly two children. If some internal has only one child, you can replace that with its child, and by doing that, the total cost doesn't increase. Okay, so you please read this. I will upload the slide also. Okay, using this lemma, all this
Sir, the
lemma.
interval, so the interval problem slides and the knapsack problem slides, sir.
I will upload today. I will
Okay, sir.
upload.
Okay, sir. And the recordings, sir, you told that you will send us some recordings also, sir, of
Okay,
I
okay.
don't
No,
remember the
no.
topic.
I have uploaded the recording of the means interval trees, etc., but not the fractional knapsack problem. I will upload today. Okay.
No, sir, I'm not talking about those. Sir, you said, sir, when I called you, you said that you will record some lecture and send to us, sir. You told us that if you have any doubts, I don't remember which topic it was, sir.
No, I have uploaded that thing in the
Okay, sir.
Moodle. You check it.
Okay, sir. Okay,
And
sir.
I
Okay.
will upload, please, all of you. I am saying that I will upload the basic graph theory, means graph algorithms. Okay, that
Okay,
means
sir.
BFS, GFS, that you already know, and you will be able to understand using the slides.
Okay, sir.
So please you read this lemma, and how it is very easy, but you should know the proofs, how, why it is optimal. Okay, or you can follow any books. This is the standard algorithm, Huffman coding. It is not the algorithm by me or you, by Huffman. Okay, today stop here.
Okay, sir.